Yes, hello, good morning. Welcome to this World Resources Forum 2025 session on critical and strategic minerals, prospection and processing technologies. My name is Michael Torst. I'm Professor for Sustainable Mining Technologies at the Technical University Leoben in Austria. We have about 60 minutes time for these sessions. We have 5 very interesting presentations that are just now coming up on your screen with presenters from a wide range of countries and even continents. And I'm really looking forward to those presentations. I will introduce them as we go along, and introducing the first of our speakers. First one is Terence Gard from the Oxford Centre for Mission Studies in the UK. And Terence will present to us a paper on the use of an appropriate prototype gravitator concentrator in artisanal and small-scale gold mining in Kenya. So Terence, the floor is yours. Please start with your presentation.
Thank you very much. So if we can then move on to the first slide of my presentation. There we go. Thank you very much. So I was born and raised on various mines in Zimbabwe. I did a degree in mining engineering at the University of the Witwatersrand in Johannesburg. Went on to do a master's degree in leadership and management academy in Harare, where I looked at mine management. And then finally, I did a PhD here in London at the Middlesex University, really looking at justice, a biblical view of justice, hence the earlier reference to the Oxford Centre for Mission Studies. And so I was looking at biblical justice as it could be applied into the artisanal gold mining sector in East Africa in particular. So I've spent my entire life in and around the mining industry, but it's the people involved in mining who I care about the most. The organization that I represent, Global Community Miners Forum, represents artisanal miners who prefer the name community miners. It started in Indonesia and now has members throughout Southeast Asia, Africa, North and South America. So next slide, please. This picture shows a typical lifestyle of women miners in Africa. It takes hours and hours of work to retreat tailings dumps, which they are doing, and you can see the mess of the tailings dumps around them. And because it takes so long, you often have mothers appearing with babies, as you can see right there. And you can see that it's a very hard, it's a lifestyle that just occurs in the middle of villages, in farmlands, in rivers. It's just a phenomenon that's enormous now, widespread throughout Africa and the developing world. And there's a typical picture of the lifestyle of women miners in artisanal mining. Next slide, please. Here we go. And so again, you can see this is now thinking about their livelihoods rather than their lifestyles. What you can see here is that it's hard labor. Everything is muddy. Everything is mucky. It's very inefficient. To earn a few tenths of a gram of gold, which is the typical take home after a day's work. It'll take many hours to retrieve perhaps half a gram or 3/4 of a gram of gold. And that's not a lot of money, but it's immediate money. At the end of the day, you can trade your gold for immediate cash, and that's a massive attraction for artisanal gold mining worldwide. But it's not an easy lifestyle. It's not an easy livelihood. It's hard work. Next slide, please. So at the bottom of the trough, as you saw in the first slide, there are blankets, and those blankets catch the heavier minerals that flow down the trough. Those could be any kind of heavy minerals, but certainly include gold particles. Blankets are then washed into a plastic basin, which is then eventually tipped into a hand pan, like you see here. And then not only are the concentrates and water in the pan, but also liquid mercury is added into the pan. And then the contents are swirled around. And what happens then is that the liquid mercury amalgams with the free gold particles and eventually forms a paste. The rest of the contents of the pan are tipped out into water, as you can see right there, which could be a pond, it could be a local river. And so, of course, some free mercury will go into that. The ball of mercury gold amalgam is then heated, usually over an open fire because of the low boiling temperature of mercury. And then the mercury escapes into the atmosphere and then settles on any cooler surface. Could be plants, could be huts, could be in the lungs of people even. And so the mercury then lands in the local ecology, secondly, not only through the water, but also through the atmosphere. However, the real issue here is not just mercury, although my paper dwells on the mercury side of things in the full paper and even the abstract. The issue here is that you can't just deal with the mercury by adding costs on to the miners' equipment and processing costs, operating costs. They just won't have that. They need to see an overall system that improves their livelihoods, improves their lifestyles, as well as improving the local ecology by reducing mercury. And so next slide, please. Now, what's happened in recent months is that an organization in Johannesburg called Appropriate Process Technologies have recently built a prototype device called a mini gold catcher. And you can see it there in the picture. What it consists of is the outer drum. You can see the red drum, but inside there's a spinning drum with ribs. And as that drum spins, the centripetal forces increase the power of gravity by 9 and trap the gold particles in ribs inside the interior spinning drum. That then is washed out onto that second sluice you see there, a very simple, properly designed mechanical sluice and mechanical system. And this device rapidly processes the tailings dumps very quickly. It also gives much better efficiencies because it's 9 times the force of gravity. It also reduces the amount of mercury that's used because it's just by recovering more gold, the people use less mercury. And so this is a very, very significant advance in the world of artisanal gold mining. And as a result of this, I have personally bought 2 of these prototype devices. Only 2 have been sold so far, to the best of my knowledge. I've bought both of them. One is there in Kenya, as you see the picture. The second one is in Harare, where it's all in Zimbabwe, where it's also undergoing field testing near Harare. Next slide, please. Bearing in mind the above stages in the processes of extracting gold, the Mini GK is designed to replace the tedious, inefficient, and labor-intensive work of sluicing. It is quick, requires less labor, gives much better recoveries, and leads to the miners using less mercury. But it's only the first part of a mercury-free system. There are other ways after coming out of the mini gold catcher and the gold grader sluice, which you saw in the first picture a moment ago. And there are a series of different devices and methods to immediately cut out mercury from this point on. But the most important thing to note, and I've put this in my abstract of the paper, which has been published already, is that miners are not interested in technology that adds costs. They're not interested in technology that requires heavy maintenance, that requires operators, professional operators. What they really want is equipment they can use themselves. And there you can see in that picture, miners queuing to use the mini gold catcher, both men and women. You can see the basins I was talking about from washing the blankets. That is then tipped into the mini gold catcher, which then in just a few minutes does the work of many hours of hand labor. And then from there, the people can then use other systems to become eventually mercury free. Right, last slide, please. So thank you very much. As you can see, there are better livelihoods, lifestyles, and we believe better impact or less impact on the local ecology by using this device. The question is, of course, scalability. I have two of these devices. They are prototypes. They're in test work in Africa, Zimbabwe, and Kenya. But so far, it's a bit mysterious as to how to make this device become more popular across the areas where they're working now, the nations where they're working now, and eventually into other parts of Africa and where artisanal gold mining is occurring. Particularly, the big worry, of course, are the lungs of the world, the Congo Basin, the Amazon Basin, and throughout Southeast Asia. So anyway, if you're interested in what I'm doing and you'd like to contact me, you can use that Gmail address, or you can find me on LinkedIn at any point in time. And that's a little bit about who I am. My NGO organizations called Foundations for Mining. As a result of my PhD, I was able to write a book called Mining God's Way. You can Google that and find that easily enough. And I'm part of the executive of Global Community Miners Forum. Thank you very much again for listening to me, and I hand it over to our panel leader. Thank you, sir.
Thank you very much, Terence, for your presentation. I'm opening up the floor for one question from the audience. Is there any questions? I think there is a posting in the Q&A question for Terry. What kind of gold ore can be processed in this? Because primary ore needs to be crushed first.
Yes, thank you. So you can, it requires free gold particles, and those can be free either in weathered soils, already in riverbeds where they've been washed down by the local water system, water courses, or as the person has noted, the primary ore, when mined from underground or from open pits, needs to be crushed first to liberate the gold particles. So yes, it does require free gold particles for the system to work.
Mm-hmm. Okay, good. Thank you very much. Terence, we might come back to you at the very end, depending on time. But for now, we'll move from gold to uranium, and it is my pleasure now to welcome Silas David from YES in Namibia to give a presentation on utilizing GIS-based geostatistical algorithms to predict uranium deposits in the Erongo region. So, Silas, the floor is yours, please.
All right, thank you. A very good morning, everyone. I'm Silas David, all the way from southern part of Namibia, which is also a southern part of Africa. So it's my pleasure today to, to be part of you guys to give a presentation on utilizing GIS-based geostatistical algorithms to predict uranium deposits in the Erongo region, which is a coastal part of the country, which is Namibia. Next slide. So basically, just to go through the steps of what we're gonna cover through this presentation. So we're gonna start off with the introduction, just to introduce this topic to the audience. And also we're gonna look at the methodology. What type of methodology did we utilize to come to the results? And also we're gonna look at the conclusion, what we have concluded based on these findings. Next slide. So basically, Namibia is on the basically on the western part of Africa. If you can see on the map, so Erongo region is a coastal area whereby it's situated in Namibia, and this specific region or provinces, what other people might actually put it, is actually one of the biggest uranium producers in Namibia, and also one of the third, if not the fourth, contribution to uranium across the world. So Namibia's role is a major global supplier of uranium, which is part of the third supplier to the uranium industry across the world. So it's also very important that we need to also explore, the targeted uranium reserves, which is within the Erongo region. So how we came to this is that the Geological Survey of Namibia have mineral occurrences which has been explored in the past. So I used these uranium occurrences data just to determine where can we actually predict uranium occurrences based on what was already discovered within the region. So the geological context is also much of that importance that we need to also look into. In which formation does the uranium actually hosted, and also in which veins that we can find these uranium occurrences, and also how can we also in that instances we can actually predict the uranium occurrences throughout the region. So basically we used these two, which is a GIS, geostatistical method, which is a GIS-based tool that we used with ArcGIS 10.6 at the moment. And this geostatistical method, it actually uses different types of geostatistical method to actually predict the nearest occurrences of uranium, using which one actually causes less errors in terms of this method. Next slide. So the uranium prospect in the Erongo region. So it's important that we need to document the occurrences. And just like I explained earlier on, we acquired this data from the Geological Survey of Namibia, which is now always hosting past exploration data of where actually certain minerals or commodity are actually found across the country. So taking into account that the Erongo region is actually rich in uranium, so we actually used this Erongo region just to actually analyze of how we can actually predict more minerals occurrences in these instances. So the spatial representation across the Erongo region also plays a major role regarding this. And also what we also look into that through this, we need to have the data quality, and also to delete out the outliers, and also data which are not actually that speaking to the topic. So throughout this accessibility and data quality, we actually deleted some data whereby it had no value in terms of depth of uranium occurrences. So that's also another part of whereby data quality also plays a major role, because at the end of the day, we do not want our geostatistical model to give us a wrong interpretation. So it's always very important that we need to clean our data for this. Next slide. So the geophysical methodology for uranium exploration in Namibia. So we look at the structural analysis. So whereby we use the correlation for the semi-variograms, whereby we also use the analogy to say that birds of the same feather actually flocks together, and that's how whereby these that's also whereby this method was used. We also did the exploratory data analysis just to give out, understanding the structure and also the normality of the data, and also likely to apply the statistical prediction using the statistical method. Next slide. So when it comes to the results of this, there are certain things that we actually encountered, valuable insights, whereby we actually got the available insights of where actually can you predict certain uranium across the region, and also for further research, whereby we can actually build on this research and also allow other researchers also to build on what we have found, because that's part of the science, whereby we need to advance each other's research, and also significance correlation, whereby we also looked at how significant this correlation actually going into about this. Next slide. So basically, throughout, there's different types of methodology that we used. So as you can see here is the ordinary method, and also the digestive method. And the points, those are actually the uranium occurrences that we actually outlined. And this is actually on the legend there. It shows that which depth actually the uranium is occurred. If you could see here, the whole region seems to be red, but we'll go further and look into that, which one actually shows better results. Next slide. And here we also have the universal method, and also the indicator method, which actually shows the prompts of where actually the prediction of certain drilling logs can actually be found around around a region. Next slide. So these are the method comparison that we also got. So we look at the certain errors, row mean square error, and also the root mean square standard error, and the mean standardization error. So this what actually what we got throughout our analysis. And for that, we actually came to compare and found the results, which is on our next slide. So throughout this, we indicated that actually the indicator has the highest accuracy due to the lowest error, and then that was followed by the universal geostatistical method, and then the third prediction was the ordinary method. So indicators actually showed the highest lowest error in terms of the prediction. Next slide. So in conclusion, it's very important that we need to take into account that mineral exploration strategy actually very important in terms of geostatistical analysis, because you can actually see through prediction where is where, and also with that you can also take into account in terms of resource management, and also to make better decisions according to what minerals can be explored and where it is found. So with that being said, thank you very much for your time.
Thank you very much, Silas. I would ask you, in the interest of time, which of course is not our friend already just after two presentations, if there is any questions, please put them in the chat, and maybe Silas, you'll respond to them in the chat. If we have time left at the very end, we might come back to those questions as well. That said, we move on to the next presentation, and next up in our line of speakers is Bio Antica from the University of Queensland, who is going to talk about quantifying an alternative source of sand from energy critical ores, the case of ore sand. So Antica, please start with your presentation.
Thank you, Professor Michael. I'm going to pull up my screen. Right, so I'm going to present about quantifying an alternative source of sand from energy critical ores, the case of ore sand. I think ore sand is such a very new term for everyone as well, so I'm going to get through that about what exactly ore sand. But before I start my presentation, I would like to acknowledge my supervisors who've been helping my research so far. So this is one of the very familiar figure. I'm pretty sure everyone's aware that energy transition minerals is a backbone of the decarbonizations. From the figure is talking about the distributions and proportion of the different minerals needed for different renewable energy technologies, and we actually contribute pretty much to these energy transitions and decarbonizations. But also we face a dilemma situation as well. In the way of us producing minerals, we produce huge numbers of waste. One of the examples of the waste that we produce is tailing. 13 billion tons of tailings we produce every year. And if it's not managed properly, this is the graph on the right side. On the right side is basically discussing about the amount of tailing disasters that have been occurring since 1915. And so far, there are 2,650 people have died because of the tailing storage facility failure. And also in total of that failures is coming from the 257 tailing storage disaster. And lots of the biggest financial consequence as well happens because of that. Then the questions now, have we done anything as a mining industry in terms of the tailing management? I think mining industry have done quite a lot of jobs, but the dominant work that we've been doing right now is mostly in reusing and also recycling solutions. If you look at academic papers, it's 18,100 discussing about reusing and also recycling. Meanwhile, it doesn't reduce the amount of tailing generated every year up until now. And also in many cases, reusing and also recycling tailing requires further processing, and some of the business case happens from the different company. They said that it costs more money when it comes to reusing and recycling. And there's one paper as well mentioning that in total commercial, the numbers of the tailing management innovations there is in reusing and recycling, it's only less than 10 of these innovations. Then the questions now, if you look at the waste management hierarchy, the very on top of or most preferred solution is waste preventions. Maybe this is a time for mining industry to also think about how do we stop the tailing generation from the source, at the same time also looking at what we can do for the existing tailing. If we're talking about waste prevention solutions, the figure on the left discussing about the realization of waste prevention only happen if we realize that out of all minerals that we mined, as an example, you see a lot of dumpsters in a mining site, all of those minerals, only minor percentage of that minerals actually targeted minerals. For instance, if you look at the figure here, only 0.1 until 0.5% are copper as an examples, and even zinc, only very minor percentage as well. Then where is the majority of minerals going? So the majority of the minerals going to tailing storage facility. I pull out numbers of the data from a different commodity. You look at from the right figure here, basically most of the minerals that been discarded, not making use, and in a tailing storage facility is silicate minerals. Silicate mineral is the main components of sand. And now if we talk about sand, it's also definitely very important resources. Sand and gravel are second most consumed resources after water, 15 billion tons per year every year. If it's hard to imagine how big is 15 billion tons, then we can imagine like we consume it every day, 18 kilograms per person globally. And it's not going to be decreased. The demand of sand will be increased 45% between 2020 and 2060. I come from Indonesia. The extractions happens a lot. And the photo on the right side is basically what happens if you extract sand from the river sand, from the sea sand, a lot of bridge collapse, a lot of life being destroyed, a lot of erosions, water quality, even the income sources of people also being at stake. So UNEP mentions that maybe it is a time for us to find the alternative source of sand, which is what we call as a manufactured sand. Bear in mind that I mentioned about at the same time we need to find a manufactured sand or the solution of a sand because the demand is increasing. But if you look at to what mining industry operating now, there are many silicate minerals is not being used or extracted from the mine industry. So this is what the Olsen is talking about. So Olsen is a type of manufactured sand. We source it from the silicate-rich ore body. We produce it as a byproduct, which is the silicate minerals, coming from the mineral ore processing before it becomes tailing. If you look at the productions flow sheet here, Olsen is basically, we just need to add one more mineral processing circuit here, and then in order to produce or to extract Olsen as a byproduct. So most of the questions happened insofar in our interaction. Is it tailing repurposing or is it from tailing? Then the answer is not tailing repurposing or even tailing, because it's a byproduct from the ore body itself. But if he also mentions about replacement to natural source of sand, then we need also to look at the main characteristic of sand. So in my research, we're basically trying to produce our sand that is suitable for different market needs, because if we wanted to use it for construction, for different needs, then it needs to fulfill certain different characteristics. Some of the main characteristics here is particle shapes, particle size distributions in mineralogy and chemical compositions. The figure on the right is basically the comparisons of what we have tried so far. So Olsen has been produced insofar, the first Olsen is in Vale Brucutu, it is in Brazil. The second trial that is proven technical feasibility in producing Olsen is New Moncadia, is a copper mining industry. The particle shapes of the Olsen, if you look at the yellow and also the green, yellow and also the blue one, they're actually very close to the river sand particle shape, which is in sub-rounded size, in comparison to the conventional manufactured sand, let's say from quarry as an example. So in that sense, Olsen is having a proof of technical feasibility to replace natural sourcing sand even better compared to manufactured sand. And the reasons why this characteristic is important, because not only it is to decide in which application of sand can go for, but we also can be used for, because the different characteristics prove a different geotechnical characteristic. That's why it's also important. But what happens right now in the mining industry in terms of the byproduct itself? In our research, we find three aspects. The first one, there are many research about byproduct productions. I think previous presentation discussing about indium, which is also one of the byproduct, can be produced from the byproduct as well. Werner also discussing about how do we produce byproduct and also how do we calculate byproduct. I think if he mentions that Olsen has positions to replace naturally occurring sand or manufactured sand, then the first question that always comes is how big is the ore sand? What's the potential of ore sand? How big can we avoid the waste or tailing itself? So if you look at here, what happened in the mining industry right now, byproduct itself is recognized by the mining industry, but in terms of the resources, they're not really estimated by the mining industry. Reasons why, either first, because there's no incentive for them to estimate the byproduct itself, or even second, because it's considered less economic value in comparisons to the primary commodities such as copper, nickel, and the other primary commodity. We also find that if we wanted to calculate ore sand as a byproduct, we use the existing framework as a resource and reserve estimations. The first thing that happened is actually they are not valued by the cut-off grade. When I was working as a mining engineer, we look at some minerals. There's a cut-off grade for us to decide how big and how much is the minerals. Ore sand doesn't value by a cut-off grade. So we value ore sand based on a characteristic such as physical, chemical, mechanical, and also environmental properties. So the existing framework doesn't fit into, it doesn't fit if we use it for to calculate the resources and also reserve estimation of the ore sand. The other factor we found is that to convert from the resource to reserve estimation, we use what we call as a modifying factors. For this ore sand itself, proximity to the market is one of the additional modifying factors that we need in order to calculate the reserve estimations. So this is the method of quantification that we found out so far. And also this is the flow sheet about how we produce ore sand. This is the flow sheet of mineral processing from New Moncadia in Australia. So we look at from the ore body itself. So the sampling point of OSEN is actually from this site. If we started from the ore body, the resources is called as an available resources. So it's basically the amount of minerals needed for the sand itself exists within the ore body itself. I mentioned different characteristic of sand, which is chemical composition is one of that. It is something that we can look as well to calculate the available resources. We use geological data. We also use ore body knowledge as well to calculate this ore sand. And then to convert it from available to potentially accessible, then we look at the whole mineral processing circuit, because the biggest influence of this is that it can be produced from different stage of the mineral processing circuit, and different mineral processing circuit has a different recovery rate. If you go to comminutions, if you go to flotations, they have a different recovery rate, and it will be quantified in potentially accessible stage. And if you go to the accessible stage itself, it will use, the difference is that from potentially accessible, the recovery rate we are using is the recovery rate from the maximum ability for the machines. Meanwhile, the accessible is more into the existing or the past historical and operational data from the mineral processing circuit. We also found that if in ore body, if we notice there is a radioactive materials, then it is less likely for us to be able to produce ore sand. But if they have a high sulfide content, then the only mineral processing circuit can produce ore sand if they have a technology called as a rougher flotation, because that's where the desulfurization will occur. So that's our finding so far. If you're keen about ore sands and wanted to ask, we're happy to connect. Thank you.
Thank you very much, Bioantika. We have 1 minute for questions. So is there any very immediate question? Otherwise, again, I would encourage you that I saw that in the chat, there has been already a back and forth between questions and answers. So use again the chat also if there is questions to Bioantika now. We'll stay in Australia for our very last presentation, but we move from Queensland down south to the University of Melbourne. The last in the lineup of our speakers in this session is Tim Werner, and he's gonna present about global cadmium resources and assessment of mining toxicity potential. So Tim, please, the floor is yours.
Thank you so much, Michael, and thanks also to the other presenters. They were really interesting presentations. My presentation is about cadmium, and so I'm just going to start off by talking a bit briefly about what it is and how it's used. I'll go through what are the key gaps and questions that I was addressing. I'm going to talk a bit about resource accounting and risk assessment, and then I'll present some findings from a study on cadmium. So although cadmium has technically been mined for centuries, it was only really discovered in 1917. And at first it was used in rust plating. And then by the mid-20th century, we started to use nickel cadmium batteries for cars. And then around the 1960s, a lot of concerns emerged around its usage. But then there was a recent resurgence again where we started using cadmium in rechargeable nickel cadmium batteries. So that's what a lot of the rechargeable batteries were in electronic devices before lithium batteries came along. But more recently, there's been a bit of a resurgence of using cadmium in cadmium telluride photovoltaic cells and in SIG cells. So in this square here, the World Bank thinks that in future, somewhere between maybe 13% to maybe 2/3 of the solar technology mix in future might require cadmium. And the IEA thinks that, okay, there's going to be a significant growth in demand for cadmium. So that's the power of cadmium, but there's also the poison side. So environmental exposure pathways for cadmium are a major concern. It bioaccumulates, it's incredibly toxic, it can cause cancer, and several studies have identified serious environmental and health-related risks around zinc-producing mines, smelters, and refineries, because cadmium is produced as a byproduct of zinc, like indium. So on the right is Jinzu River in Japan, which is one of the most famous cadmium poisoning events, where it basically got into the river from mining operations, and accumulated in rice crops. So there's two sides to the story of cadmium. On the one side, it's a resource, but on the other side, it is a very concerning pollutant. So given these aspects of demand and risk, we've seen really interesting patterns of production emerging. We've seen total production stagnate as cadmium is phased out of virtually every application except solar technologies, and we've seen the price drop dramatically over time in real terms. But despite these weaker total demand signals, we're actually likely going to be seeing more cadmium coming out of the ground simply because it exists in zinc deposits, and we will continue to mine zinc for use in steel, for example. So projections of future zinc use are going up, which means regardless of the fact that we don't need as much cadmium as we used to, it's still going to be mobilized out of the ground, and it is still an environmental concern. The first gap in the study that I wanted to address was, where are the cadmium resources and how much is there? And when you look at the literature, there's a lot of disagreement, basically. So this study here, 0.49 million tons, 500,000 tons, and another study down the bottom, up to 100 million tons. So there's a wide range of uncertainty. Then you get some studies saying, well, the USGS, for example, they don't really report on cadmium resources anymore. They say quantitative estimates for cadmium reserves and resources are not available. That's what they say in their reports. And then you've got this other one, the one at the top, saying cadmium ranks 13 among 76 elements for crustal depletion potential and 8th for abiotic depletion potential. So we're getting kind of mixed signals here. Some saying, well, maybe there's some depletion potential, others saying we don't know, and other studies saying, well, actually, there could be 100 million tons out there. But the problem is that there's no consistent methodology behind these studies, and there's no traceable methodology. So that was the first gap. And because of that, we have a poor understanding of where these toxicity risks will actually present worldwide. So we simply have not had the data to be able to track where is cadmium being produced, where is it entering the environment. So that was the second kind of gap that my study sought to address. So what did we do? We did it the long, boring, slow way, which is to build up a database of cadmium deposits one by one and try and figure out as much information as we possibly could. Over a few years, we reviewed thousands of mining company reports, technical reports, websites, government sources, journal papers, and we tried for each site to gather as much information as we could. What's the name of the mine? What are its coordinates? Who owns it? What type of geology is there? What resource and reserve data is there? And citing all these sources so that it is at least traceable. But as beautifully pointed out in the previous presentation, sometimes for these byproduct metals, companies don't always report how much there is. So in this case, we need to figure out what don't they report. And so fortunately, there are strong geological relationships between cadmium and zinc and lead. And so when we look at a deposit type and we know how much zinc there is, we can make a reasonably good guess at how much cadmium there is too, even if the company is not reporting it. And so we looked at all sorts of cadmium geochemical data in hand samples in sphalerite from 145 different deposits. And we looked at, well, what are the ratios in the deposits where it is being reported? And so our database looked like this at first. So these are the 238 deposits where we had information about cadmium at that site that was reported. And so about 1.4 million tons there. And then a further 689 deposits where we know there is sphalerite there that hosts cadmium, where we have made an inference about how much cadmium is likely to be there. These are the countries that actually report refined cadmium production. So we're seeing interesting geographies about who's actually producing it versus who is actually just digging it out of the ground and maybe shipping it elsewhere. And that has implications for the kind of spatial spread of cadmium toxicity associated risks, but also who's participating in the supply chain in different ways. Using data from the International Zinc Study Group, we were also able to determine which sites were actually currently active and identify their annual zinc production capacity. And from this, we calculated rates of cadmium extraction in zinc concentrates per annum. So this is a more precise view of where cadmium is actually being mobilized globally. So we thought that this was a more traceable and more geographically explicit view of cadmium compared to what those previous studies were showing. And we can break down who has resources and reserves by different country, by different levels of certainty based on what's actually reported versus what is estimated. So these are just the top 10 countries, but then we also have a breakdown for every country as well. So that was the resource side of things. We also wanted to assess impacts or risks. So a few years ago, me and a colleague published this study, which was a global footprint of mining. It is not completely comprehensive. I do not think it would have every small-scale mine in it, for example, but it is based on our best go of what we could see in satellite imagery. It has reasonably good coverage of larger scale mines and somewhat good coverage of well-known artisanal mining regions. So we used this footprint data and we combined it with our resource data, and we started to do some interesting spatial overlays. So looking at where is cadmium in relation to protected areas, for example. And when you have a look at where cadmium is actually reported, and you compare that to a distance to the nearest protected area, you can see there's lots of sites that are clustered close to zero. So there are lots of sites that are either in or directly bordering protected areas where cadmium exists as a resource or is being mobilized, presenting toxicity risks. In terms of bioaccumulation, we looked at cropland cover in relation to these sites. And we identified, for example, some areas of concern around India where you've got cadmium deposits or cadmium being mobilized with a lot of crop cover in the areas immediately surrounding the mines, presenting this potential human health risk. And equally, we assessed water cover in the same way. And we looked at population exposure. So we looked at population density in relation to these locations, and we find that there's roughly 3 million people less than 10 kilometers from these cadmium sites worldwide. So small in relation to the global population, but for those 3 million people, perhaps something to be aware of. So we have these kind of distributions for different risk categories in relation to where there's resources and where there's production. So that's what's in orange. So essentially the key messages from this story are that although there is poor data for a lot of these byproduct metals and the metals that may present kind of toxicity risks, we can use publicly available information out there to develop an open resource database to improve our understanding of these commodities and how they're distributed. And, you know, this is a case where even though there's declining demand for a resource, that does not necessarily mean that the impacts of extracting it disappear because it is a byproduct commodity. And you know, the other finding was that there's more work needed to address this kind of hidden toxicity behind supply chains of critical minerals. We tend to focus on the main commodity itself and where it goes, that there are other commodities, there are other impacts that are aligned with those flows. So this study is open access here. You can download the whole database. And that's all. Thank you so much.
Thank you very much, Tim. Any questions specifically for Tim at this stage? I see there is one in the Q&A from Johannes Drilsma. Hi, Johannes. Tim, could you please comment on the potential gap between presence of cadmium with the mobilized materials, actual exposure to cadmium, and manifestation of impacts due to that exposure? Are you looking in future to get a better handle on this?
Yeah, that's a fantastic question. We just wanted, as a starting point, to do a global sort of top-down view on where is it, so that we can start to narrow down on locations that may be of interest. But of course, for those locations, we have to visit them. We have to do environmental sampling, maybe surveys, to actually understand what are the on-the-ground impacts. So what we are measuring is not actual impact, actual toxicity. It is merely indicators of risk potential.
Okay, good. Thank you very much. Terence, I had one question posted for you in terms of upscaling plans with regards to the technology that you presented today from the pilots that you actually sort of are running at the moment towards mass use. Are there any plans that you can maybe talk a little bit about very briefly?
Thank you for the question. And it is the biggest issue now. Obviously, testing new technology is a sequence of events. And so what we've done so far is simply proven the technology is very reliable and it is appropriate. We've also proven that a number of immediate personnel are enamored with the technology and want to use it. They're queuing to use the equipment. But at this stage, even though it only costs about $5,000 per unit taken to the country and commissioned and set up and operating, that is still a lot of money when your take-home pay as a miner ranges from less than $10 a day. And so that is where the problem lies, is it's going to have to take either local business entrepreneurs to buy it and set it up. The miners already by themselves form units or enterprises that buy compressors, they buy chainsaws, they buy jackhammers or rock drills. And so they do have the capacity to buy equipment and as a group of people and then hire themselves out and hire the equipment out. And I'm really hoping that will be the route that we will see for this technology. But I do need to spend more time now in Africa, both in Zimbabwe and in Kenya, and really just sit with people and listen to them and see what the stories are and what are the issues that are preventing scalability. And so it's really a listening exercise I need to go out and do, because I'm not getting that grassroots information that I require right now.
Okay, good. Thank you, Terence. And indeed, thank you to all of the presenters for your presentations. As you've seen, I guess, in the audience, we've had a very wide range of presentations covering many aspects of critical raw materials, from exploration all the way to sort of the environmental, social impacts of even byproducts of critical raw materials exploitation. So thanks indeed for your presentations. Thanks indeed also for your questions. Good luck to all of you with the further research on those very important topics. Good luck with the implementation of your findings, as in the case with Terence particularly. And thank you very much to the audience for your interest in this session. With that said, I'll hand back to the World Resources Forum for the further proceedings. Thank you very much and have a great day. Bye-bye.